Now let's solve example 5.9. and in example 5.9 we have been given a solenoid and we are supposed to find out the magnetic field inside and outside of this solenoid. So solenoid is a cylindrical shape, and on the top of it we are having a winding. Now this winding, we will have to discuss a little bit this thing. These windings are very close to each other. Now the reason that they are very close, because we want to consider each winding is a circle, a complete circle. So for applying the circumference relation in the Ampere's law, we are considering it like this. Now what means all the current is going around this solenoid, this cylinder, but what about its current in the direction of the axis of a solenoid? So when we consider complete circles, but the circles are also joining each other, so there will be some component of current which is going along this one. Or for example, if we consider in aluminum foil around this cylinder and we apply some current, so that current, the surface current K, which will be going through this whole aluminum foil, then it will be having the axial contribution as well as the circumferential, means going around this one. So in that case there will also be some axial current contribution. So the question is that what is the contribution of the current which is going around this one, around the cylinder, and going along the axis. So going along the axis, the current is considered negligible, and all the current, the main contribution is from that winding, is from that wire, which is basically causing the magnetic field inside this solenoid. So we will consider this one to solve that how much is the magnetic field inside and outside of this solenoid. Solenoid we are using just like an inductor we are having, so it's in the form of a solenoid. Inductor is a solenoid. So let's solve this thing. The very first thing that we will experience here is the direction of magnetic field. In which direction the magnetic field will be. If we say that current is going, let's say, in this direction, then the magnetic field is going around it. And if the current is going around like this, the magnetic field will be directed this way, or if the current is going this way, then the magnetic field in this direction. So we are having here that the current is basically going in this direction. So it is like this. So the magnetic field, if this is the z direction, then the magnetic field is in the z direction, and it is along the axis of the direction of the axis of this solenoid. So what about any circumferential field? So we don't have any circumferential field, and that we will explore here. Do we have a magnetic field outside of this cylinder? So the magnetic field outside of this cylinder, then we will consider an Ampèrian loop here, and we will come to know that there is, as this loop is enclosing no current, means to enclose the current we will have to enclose it this way. So the magnetic field in that case will be equal to 0. And then outside, even if we consider this the square loop, the Ampèrian loop, then this loop which is its side is a distance a from the axis and the other side is a distance b from the axis. So this loop is also not enclosing any current, and that's why the magnetic field is to be 0. And when we consider here, then it is enclosing some current and we will have the magnetic field here. So going for all this calculation, this was the earlier discussion that was necessary in order to understand the direction of the magnetic field, the the axial contribution of the current, and so on. So considering, let's say we consider here, for this is the solenoid, current carrying wire is there, which has been wound around this, and we are going to calculate the field at a distance s outside the solenoid. So we can write the Ampere's law, and the Ampere's law is we have written down here that on a closed loop we have P dot dl, and this is equal to mu naught times the enclosed current. So here this will come out to be, this is the B phi. I'm considering the magnetic field around the circumferential direction are the phi. So I can write, this implies that B, and with this B I can write phi, and 2 pi s is the circumference of this circle, this Ampèrian loop that I have considered, and this is equal to mu naught time how much current is enclosed by this loop. So the loop is enclosing 0 current, and this implies that B phi is equal to 0. And now, if I consider the other geometry, which is the geometry here, means outside, means another way I'm doing this calculation. So I'm considering this square loop or rectangular loop of length L. This is basically square loop, but is there was a limitation in the board, so it is a bit elongated here. So this is L, and the length of this loop is L, because this length will be counting the enclosed current. So I can write that for the loop 1, I can write that one side, because this one, it is having no contribution, this side and this side. So we are having, this is the one contribution, and then this is the one contribution. This is a distance A and this is a distance B. So I can write that B dot dl, this is equal, now this will be B, and the value of B8 A and minus B, the value of P8 A minus the value of P8 B times L, because the total length here, when I go around the loop, the total length here is L, and this is equal to mu naught, and how much current is being enclosed by loop 1. So loop 1 is enclosing 0 current, and again we have that BA minus B and L will drop. So this is equal to 0, so it means BA is equal to B 8.B. It means that the value of the magnetic field at point A is the same as the magnetic field value at point B. And we know about this magnetic field, that magnetic field as we have calculated here, this magnetic field must drop as you go away from that current. So it should drop as 1 over S. And here we see that the magnetic field at this point and this point is the same. And this is basically only one situation. And that situation is that the magnetic field is 0 outside, and that's why we are having a 2 points the same value, and that same value is basically 0 there. So now coming back to loop 2, and in loop 2 we have now the loop is going inside of the solenoid, and this is completing the whole loop. So it is enclosing some current, and I can write that B dot dl is equal, B is the value of magnetic field, and L will give me the total length, which is the length of this loop. And this is equal to mu naught. And now, what is the enclosed current? One thing, the enclosed current is equal to 1, that is I. Then, how many turns are there? And the turns are small n here. So n times I is the loop's current, and then for how much length this is going. So the length for which it is going on this side is L. So on this side we are also considering this equal to L, because this is enclosed by our loop. So this is mu naught and NIL. So this is the total enclosed current by our Ampèrian loop. So L is cancelling on both sides, and we are having the magnetic field B equals to mu naught and N times I. N being the number of turns per unit length. Here we are having closely amount turns per unit length, and this gives us the total current here. So we have the finally, if I look at the direction of this, then inside the solenoid this field is in the Z direction, because current is going this way. So Z direction is here, and it is equal to this. And outside the solenoid we are having this equal to 0. So we call this is the inside the solenoid, and this is outside the solenoid. So the magnetic field is the magnetic field inside here. If we consider infinitely long cylinder or solenoid, then the magnetic field lines will be exactly parallel to each other, and we will have a very uniform magnetic field here inside this one. But for a finite cylinder or solenoid, these lines will go in slightly, they will slightly deviate here, and we will have some fringes effect there. So in the middle we are having the magnetic field exactly parallel lines, but as it goes to the edges, then the edges effect will come in, and the magnetic field will be slightly, you can say, deviating from that point, and will not be considered as uniform at the edges. but in the center, or for an infinitely long solenoid, this field is considered is uniform or completely in a plane form. So this is for solenoid. We have this thing, and then in the next example, we will consider the toroid example. And inside the toroid, what is basically a toroid? This solenoid is joined, means the ends are joined together. So that gives the geometry of a toroid.